Hi everyone! Last time we talked about how to solve separable differential equations. So today let's talk about some applications. The first application, natural growth and decay. Suppose P of t is the number of individuals in the populations. It could be of humans or insects, bacteria, or a sample of materials. And the rate of change of P of t is proportional to P of t. Okay, so what does that mean? Rate of change of P is dP dt. It's proportional to P of t. It means dP dt is a constant times P of t. So we get the following differential equation. And with the initial condition that P of 0 is the populations at time 0. So P of 0 is P0. If k is positive, then we have population growth. If k is negative, then we have population decay. So how to solve this differential equations? Let's see. We have dP dt equals kp. Alright, it's separable, so let's move the p to the left. So we divided both sides by p. And let's multiply both sides by dt. Alright, what's the integral on the left? Well, the integral on the left is like 1 over p. Integral is natural log of absolute value of p. The right hand side we have kt plus c. Okay, and then in order to get rid of the natural log, we want to both sides raise to the e power. So we have e to the ln of absolute value of p equals e to the kt plus c, but e and natural cancel. We have absolute value of p equals e to the kt. Here we can use the properties of exponential function and we can get e to the c, right? So notice that e to the c is greater than 0, but because of the absolute value, p could be positive and it could be negative, right? And furthermore, at the beginning, when we divide it by p, we actually lose the solutions, okay? We lose the solution p equals to 0. So when we divide by p, we lose the solution p equals 0. And p equals 0 is a solution because p prime is 0. And so when we plug in here, we get, it satisfies this differential equations. Okay, so now what we're gonna do, we're gonna rename e to the c to be a new constant. Okay, so we rename new constant. And it can help us to take care of, so it can help us to get rid of the absolute value, because p now it could be positive or it could be negative, because d now could be positive or could be negative. So it can help us to get rid of the absolute value. And second, it can help us to gain the solution p equals 0 back. Because now we can plug in d equal to 0, then we get p equal to 0. So now this is good. So this is our solution. And this is our general solution. Notice that this differential equation is linear. So we get this guy is the general solution. Alright, and we can now plug in the initial conditions, p of 0. So p0 equals e to the 0 times d, but e to the 0 is 1, so we get d equals p0. Now we plug in d equals p0, then we get this solution. Okay, so this is the solution of population growth. Note, if k less than 0, we have population decay, right? The population decay, the half-life of a radioactive material is the time required for half of it to decay, okay? So, i.e., if T1 is the half-life, if the population at T1 equals half of our initial population. So this is the definition for half-life. Alright, let's continue. Okay, example 4. Suppose the population of a colony of bacteria increases exponentially. At the start of an experiment, there are 6,000 bacteria, and 1 hour later, the population has increased to 400. How long will it take for the population to reach 10,000? Okay, let's see. Okay, let's write down the information. Alright, so because the population increased exponentially, we know we're gonna use this formula. By the way, in the exam, because we have already derived this formula in class, you don't have to derive again. You can just use it. So P of t is P0 e to the kt. Just use it. Okay? And P0, so at the initial population is 6,000, right? And then 1 hour later, so T is the number of hours, right? 1 hour later, the population increased, so 6,400. And then our goal is to find the time such that the population of that time equals 10,000. Okay, so now let's see. We plug in P0 6,000, and then this information will help us to find the K. Okay, so let's plug in and find K. So P1 is 6,400. So we plug in T is 1. Alright. Oh, then we see e to the k. E to the k is 6,400 over 6,000. And let's see, what is the common factor? Oh, 4, right? 4, 16 over 15. Okay, now how do we find k? Get rid of the e, right? So we apply natural log on both sides. Natural log e to the k is natural log of 16 over 15. Natural log e canceled, so this is just k. And leave your answer like this at this moment, so don't plug in your calculator and get a bunch of decimals. We want to have exact answer at this point, okay? And then how long will it take for the population to reach 10,000? So we want to find the time such that P of t, now P of t is 6,000 e to the kt, but k is ln of 16 over 15 t. We want to set this guy equals to 10,000. Here, a common mistake is student will cross out this. No, don't do it. Okay, because there is a t there, you cannot just cancel the ln and the e. Okay, be careful. So what do we do here? Let's isolate the exponential term. So e to the ln 16 over 15t equals 10,000 over 6,000. Ooh, this is 10 over 6, so 5/3. Okay, and now in order to solve for t, we want to both sides apply natural log, right? Oh, I need more space. Let me move this guy to the left. Okay. All right. when we apply natural log, we get the left-hand side is ln of 16 over 15t, because e and natural cancel. The right-hand side is natural log 5 over 3. Okay, t is natural log of 5 over 3 over natural log of 16 over 15. Okay, so now here you can plug into your calculator. So we only plug in the calculator at the last step. Okay, then our answer could be more accurate. And let's see, ln of 5/3 over ln of 16 over 15. So I suggest everybody can pause the video and type this in your calculator. What do you get? I get 7.9 hours. Do you have the same answer? Yes. Okay, good. So let's review this example again. First, we use the formula of the population growth, right? And then we have the initial population, and then we also have one information. P of 1 is 6,400. We can use this information to find K. Once we find K, then, well, the goal is to find the time when the population reached 10,000. So we plug in the 10,000 for P of t and solve for t. Alright, let's continue. Example 5, radioactive decay. The half-life, which is the time such that the population at that time is half of the initial population. Okay, so the half-life of radium 226 is 1,590 years. Part A, a sample of radium 226 has a mass of 100 milligram. Find the formula for the mass that remains after t years. So we want to find the population function. Okay. Part B, find the mass after 1,000 years, correct to the nearest milligram. So which means we want to plug in 1,000 for the t. Okay, we want to find P of 1,000, right? And then C, when will the mass be reduced to 30? So we want to find the time such that P of that time equals 30. Okay, let's see. Initial population is 100. So P0 is 100, right? Okay, then P of t equals 100 e to the kt. Okay, how do we find k? We need to use the information of half-life. Okay, so half-life means P of 1590 is half of what we have before. Okay, so we plug in that. T is 1590, and P of that is 1/2 of our initial population. Okay, so you can actually cancel the 100, and then we get e to the 1590k is half. Apply natural log on both sides. Okay, and then what is k? Natural log of 1/2 over 1590. So far, so good, everyone. So we figure out our k. Now, good. What is the population? Well, P0 is 100. And then e to the k is natural log of 1/2 over 1590 t. So this is the population function. Okay, part B, we want to find P of 1,000. Let's see. P of 1,000. Let's plug in 1,000 for the t. Okay, so let's plug this in your calculator. what do you get? Let's see. Okay, so here I want to show you how to put this in the calculator. So let's use this online calculator. So okay, we have 100 times e to the natural log of, where's natural log? Here, natural log of 1/2. Oops. And oops. Times 1000 divided by 1590. Okay, so the answer is 64.7. Oh, find the answer to the correct to the nearest milligram. Okay, so 65 milligram. All right, and then find the time such that p of t is 30. Okay, so p of t is 30. 30 equals 100 e to the ln of 1/2, 1590t. Okay, both sides divided by 100. So e to the ln 1/2 over 1590t is 30 over 100. Oh, we can cancel the 10. And then we can apply natural log, right? So when we apply natural log, on the left-hand side, we have ln of 1/2 over 1590t equals natural log of 3 over 10. So t is natural log of 3 over 10 over natural log of 1/2, but times 1590. Okay, let's plug this in our calculator. Let's see what happened. So, natural log of 3 over 10 times 1590 divided by natural log of 1/2 is like 0.5. Okay. Ooh, 2,762 years. 2762. Wow, long time, right? Okay, so this is the radioactive decay example. All right. Okay, let's continue. So the next applications, Newton's law of cooling. It states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. So if we let T of t be the temperature of the object at time t, and Ts be the temperature of the surrounding, then we will get dt dt. The derivative of the temperature with respect to time is proportional. So K times the difference T minus T surrounding, right? And here K is a constant. And we know K is going to be negative because the change is going to be smaller, smaller, smaller. All right. And we make change of the variable y of t equals t minus ts. Then y prime of t is t prime of t. So then after we plug in this new variable, we just get dy dt equals k times y. This is exactly the same differential equation that we solved in the population model. So that's why we know the solution y of t is y0 e to the t. Now we replace by t. So Then we get on the left hand side, y is t of t minus ts. And the right hand side, y0 is t0 minus tx, and then times e to the kt. So this is how we get the formula. So this is the formula for the Newton's law of cooling model. Okay. All right. Let's look at the example 6. A bottle of soda pop at room temperature, 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After an hour, the soda pop has cooled to 61 degrees Fahrenheit. Okay, part A, what is the temperature of the soda pop after another half hour? Part B, how long does it take for the soda pop to cool to 50 degrees Fahrenheit? Okay, so here I want to ask you something. Okay. Alright, let's draw some picture. Okay, this is the, let's say this is the refrigerator. You're right here, holding a soda pop. Okay. Alright, if you want to put the soda pop from the outside to put into the refrigerator. Okay, so place the soda in the refrigerator. Okay, now what happened? What is your initial temperature? So the initial temperature of the soda pop, because it was outside, so the initial temperature is 72 degrees Fahrenheit. But the temperature surrounding, so after you place the soda in the refrigerator, the temperature surrounding is 44 degrees Fahrenheit. Okay, next story. If you take the soda from the refrigerator, so you want to take it outside of the refrigerator and drink it, or maybe just place on the desk. Now what happened? So take the soda from the refrigerator and place on the desk. So in this case, the initial temperature is going to be the temperature in the refrigerator, which is 44 degrees Fahrenheit. And the temperature surrounding, now because the soda is placed outside, so the temperature is the room temperature, which is 72 degrees Fahrenheit. So you can see that these two different stories. Your initial temperature and the temperature surrounding are different. So you must read the problem carefully, and then you can figure out which was which. Okay, so in our case, we want to place a soda in a refrigerator. So we are this case. All right, now let's see. Okay, let's see. So let's plug into the formula. So T of T minus Ts. Ts is 44 degrees. Equals T0. T0 72 minus 44 degrees. E to the KT. Okay. So now what happened? We still need one information. So let's see, after half an hour, the soda pop has cooled to 61 degrees Fahrenheit. So it means P of half hour is 61. So let's use this information to find the K. So we plug in T of 1/2 is 61. What's 72 minus 44? Is it 28? E to the K times T is 1/2. Okay, so here we plug in T of 1/2 equals 61. Alright, let's continue. 61 minus 44 is 17. So e to the K times 1/2 is 17 over 28. Now, in order to solve for K, let's take natural log on both sides. Natural and E cancel. So we get k times 1/2 is natural log of 17 over 28. Ooh, so k, we just multiply both sides by 2. Okay. If we multiply both sides by 2, what do we get? We get 2 times natural log of 17 over 28. So this is the k. Now we plug it back, then we get t of t minus 44 equals 28 e to the k. K is 2 natural log of 17 over 28 times t. Okay, so this is the temperature function. Part A, what is the temperature after another half hour? Okay, so after a half hour, it decreased to 61. So the question, after another half hour, it means we're actually looking for what? T of 1. So we're gonna use this formula. So solve for t. So t of t is 44 plus 28 e to the 2 ln of 17 over 28t. So t of 1. 44 plus 28 e to the, because it's 1, then we have 2 ln 17 over 28. What is this? Okay, let's see. Calculator right here. So 44 plus 28 times e to the 2 times ln of 17 over 28. Okay, so the answer is 54.32. So 54.32. What is the unit? Degree Fahrenheit. Okay, so sometimes you gotta be careful. We might use degrees Celsius. Okay. Alright, so that is part A. Part B, how long does it take for the soda pop to cool to 50 degrees Fahrenheit? So part B, we want to find the time such that t of that time is 50. Let's see. Let's plug in. So 50 minus 44 equals 28 e to the 2 ln of 17 over 28t. 50 or minus 44 is 6. So 6 equals the right hand side. Okay, so let's see. Now we want to solve for t, so both sides divided by 26. And let's move this to the left. Okay. Then we have 6 over 24. Oh, that's actually 3 over 14, right? Okay. Apply natural log on both sides. So natural log of 3 over 14. Well, t is then natural log of 3 over 14 divided by 2 times natural log of 17 over 28. Okay, what is this? Calculator. Oops. Natural log of 3 over 14 divided by 2 times natural log of 17 over 28. 1.54 hours. Okay, so around 1.54 hours. Okay, so this is the temperature application. So far, so good, everyone. make it too small. Okay, let's continue. Okay, last application, compound interest. So if we invest $0 at interest rate R, compounded n times a year, then after 1 year, the investment is worth A0 times 1 plus R over n to the n power dollars. And then this investment after t years becomes, so after t years we just keep multiplying more copy of it. So then that's why you see this is the power is nt. Okay, and R is the annual interest rate. And if we let n goes to infinity, then we can get a of t equals the limit a of t 1 plus r over n to the nt. So we can express this guy as we can divide it by r and then multiply by r. Then we know these two are the same, right? Because r can cancel, so we know they're the same. Okay, so but now, do you see this guy is the reciprocal of this guy? So actually, we can let m to be n over r. Because r is fixed, when n goes to infinity, m also goes to infinity. So that's why we have 1 plus 1 over m to the power m, and then times r to the rt. Okay, and it turns out this guy, when t goes to when m goes to infinity, this guy is the number e. Okay, that's why we have a0 e to the rt. So if the investment after t years, or when we compound continuously, the formula is a0 times e to the r to the t. E to the rt. Okay. Let's look at example 7. If $200,000 is borrowed at 5.5 interest rate, find the amount due at the end of 30 years if the interest compounds annually, monthly, continuously. Okay. Annually means, remember n is the number of compounding, right? So n is 1 in this case. Okay, and then we know a0 is 20,000. R is 5.5%. So 5.5% is the same as 0.055. Okay, let's see. Part A, n is 1. So, okay, now we can plug into the formula. AT is a0. A0 is 200,000. And then R is 0.055 over n. N is 1. To the n is 1, t, right? And so we want to find 30 years. So 200,000. 1 plus that is the same as 1.055 to the 30. Okay, let's put this in our calculator and see what happens. $200,000 times 1.055 to the 30. Oh, you see? 996,790. 996,790 points what? 26 cents. Okay? Alright, so this is part A. Part B. monthly, the number of compounding is 12. By the way, quarterly, then the number of compounding is what? Quarterly, how many quarters in a year? 4, right? So n is 4 in that case. So now, okay, now just plug in a of t equals 200,000. 1 plus 0.055 over n is 12, and then to the 12t. So a 30 is 200,000, and 12 times 30. Okay, let's plug this in our calculator. 200,000 times 1 plus 0.055 divided by 12 to the 12 times 30. Oops. Oh, I want to have the 30 on top. Sometimes you're going to be careful and check. Alright, so I want to have the 30. Oh, so I think I need to put a parenthesis there. Otherwise, it won't let me to put it on top. Okay. Alright. Now, do you see? Oh, that's a lot of money, right? 1037477. 1037477. And actually, it's close to this amount, but more than that. And it makes sense. If we compound more, then the money should be more, right? So 477 and 57.57. Okay, and that's a lot of number. Let's put the commas between. Okay. Okay, part 3. If we compound continuously, then we're gonna use the formula a0 e to the rt. All right, so a of t is a0 e to the r 0.55 t. So a30 is 200,000 e to the 0.055 times 30. What is this? Let's see. 200,000 times e to the 0.055 times 30. Okay, 1041395. 1041395.97. And you can see they're also very similar, right? Close. But compound continuously is bigger than that. Okay? And it makes sense. It compound continuous, of course, you get more money. Okay, in this way. So now this is the compound interest applications. So we just use the formula and then figure out what is the number of compoundings per year. And sometimes you also be careful because your R, for example, 5.5% is 0.055. And sometimes students make the mistake and say this is 0.55. No, 0.55 is 55%. That's a lot. Okay, and now we have finished all the applications problems in session 1.2 and 1.4. If you have questions, feel free to ask me. Have a nice day. Bye.